Hi guys, welcome to our fourth lecture on photonic devices. On today's lecture, we're going to cover the difference between direct and indirect gap semiconductors. We're also going to talk about the relationship between the wave vector k and momentum. And finally, we're going to start talking about carrier concentration and carrier density as well. So before we start talking about direct and indirect bandgap semiconductors, let's recall that at the end of the last lecture, we saw that there were basically three band structure pictures that could be useful: the extended zone picture, the periodic zone picture, and the reduced zone picture. And the most useful one, which is the one that we're going to be using on this course, which is the most useful one for optoelectronic devices, is the reduced zone picture. So, which is this one right here. So this is the band diagram. This is the reduced zone picture band structure, okay, for a 1D periodic lattice, as we saw. So you see energy as a function of K, and you see only one period of E over K here, as opposed to the periodic zone picture where you'd see multiple periods, or the extended zone pictures where the bands would not overlap. So you would fold this here to the right, and then you could fold, maybe bring this back here over to here, and so on, so that the bands would not overlap. But in optoelectronic devices, since we're interested mostly in band transitions from conduction band to valence band and vice versa, the reduced zone picture will suffice. And actually, we're going to be mostly interested in things that happen between the conduction band, which is the lowest one that's unoccupied, and the valence band, which is the highest one, which is completely filled. So we could only draw these two bands. And the most interesting or important phenomena will actually happen between the borders of these bands. So many times we'll just draw the lower border of the conduction band like this, and the upper border of the valence band like this, because this is where most of the transitions will take place. So as we've just stated, the most important electronic transitions will occur between the border of the conduction band and the valence band. So we can draw only these borders like this. Usually this is what we do. So the conduction band right here and the valence band down here. So the reasons for this are the following. Let's consider in a semiconductor at absolute 0 K, 0 degrees Kelvin, the valence band is completely filled and the conduction band is empty, okay, because there's not enough energy for the electrons which are down in the valence band to come up to the conduction band. So I've drawn full circles here as occupied or filled states. At higher temperatures, for example at 300 K, the heat can only supply enough energy for some of the electrons of the valence band to move up to the border of the conduction band. So I've illustrated it here, where we see that a few electrons have moved up to the conduction band, particularly the electrons at the border of the valence band, because this requires the least energy, right? The least energy difference will happen between the borders of the bands here. And as the electrons move up, like so, they will leave behind empty states, which is what we call holes, which I've represented as empty circles here. Okay, so these transitions are the ones that require the least amount of energy. And since thermal energy, on average, will provide energies around tens of millivolts, this is only going to be enough for a few of the electrons that are right at the border to make the transition. Because, as we've said, it takes much less energy for an electron which is down here to come up here than it would take for for example, for an electron that is, a much lower position in the valence band to move it to a higher position in the conduction bands. Transitions between the borders of the band are the ones that take the least energy. Also, you have large density of states, as we'll see, and you have very small carrier concentrations, so very few electrons will make these transitions. And it's most likely that the electrons that do make the transition will be the one for which the required energy is the least. Okay? So other transition processes can take place, for example, absorption of light or emission of light. So these transitions between valence band and conduction band and vice versa can happen through other processes besides temperature. Okay, so absorption, emission, but these are processes that we'll account for later. Other important information is that only electrons which are close to the border of the conduction band contribute to current in semiconductors, and only holes which are close to the border of the valence band contribute to currents. And this has to do with the probability of occupation, which is the Fermi function, which we'll see later. But basically, if we draw the band structure, looking only at the borders, what we're saying here is that only the electrons which are right at the border and the holes or the lack of electrons which are also at the border of the valence band in this case, conduction band for electrons, these ones that will be used for conducting electricity. Well, this is due to the fact that the probability of occupation of these states, close to the border, are much larger than the states which are far away from the border. So there will actually be only electrons here, and therefore they will be the only ones that will be able to move around through the solid, through the lattice, and the same goes for the holes. With respect to band structure, it's important to distinguish between direct bandgap semiconductors and indirect bandgap semiconductors. So what's the difference? The difference is going to have to do with the band structure. In direct bandgap semiconductors, the border minimum value of the conduction band and the border corresponding to the maximum value of the valence band happen for the same K. So these two things will correspond to the same wave vector K. So if we plot this, it would look something like this. The border of the conduction band, right, this point right here, and the border of the valence band, this point right here, will happen for the same K value, which is here, in direct bandgap semiconductor. And we'll see why the term direct is used later, but as opposed to this, for indirect bandgap semiconductors, these borders are not aligned in terms of K. So the border of the conduction band and the border of the valence band do not happen for the same K value. So if we make the same drawing, now for an indirect bandgap semiconductor, what we would see is something closer to this. So you could have the border of the valence band, for example, right here, but the conduction band, would be misaligned, would be shifted towards the right or the left in such a way that the border of the conduction band happens for one K value, let's say K dash, and the border of the valence band happens for another K value, K2 dash or something. So these happen for different Ks. When this happens, we say that the semiconductor is an indirect bandgap semiconductor. If you recall, on our last lecture, we looked at the band structure for silicon. And if you notice, this is what happened there. So this is what I'm talking about right here. And if you look at the valence band and the conduction band, the border of the conduction band is here. But if you compare the K value of this border to either this point on the valence band or this point on the valence band, which have approximately the same energy and could be considered the borders. In either case, there's a misalignment in K between the borders of the conduction band and the valence band. So therefore, silicon with this band diagram, or band diagram similar to this, is clearly an indirect band gap semiconductor. Okay, the borders do not happen for the same K, as we can see clearly through these 3 points here. In real semiconductors, the lattice is three-dimensional, and therefore it will be more complex. This is the case of what we just saw for silicon, right? We don't have a nice and symmetric lattice like the one we illustrated for the 1D periodic structure, but still you have similar features, and because of this, the bands can be misaligned. So you can have indirect band gap semiconductors. In indirect band gap semiconductors, there's therefore a mismatch delta K in the wave vector value between the electrons at the border of both bands. So let's look at this nicer illustration here. Here you have a direct band gap semiconductor, so delta K is equal to 0. The border of the conduction band aligns perfectly, in the K direction with respect to the border of the valence band. And here you have an indirect band gap semiconductor where you see the wave vector mismatch delta K, which is the K difference between the border of the conduction band and the border of the valence band. So this is delta K. In the figure, you also see the band gap, the energy associated with the forbidden band here. But yeah, this is what happens for indirect band gap semiconductors, and this is the wave vector mismatch delta K. So a very important feature associated with direct and indirect band gap semiconductor is that only direct band gap semiconductors, such as gallium arsenide, can be used as light sources. So if you're going to build a laser or an LED, you need to use a direct band. In general, you need to use a direct band gap semiconductor. If you're going to build photodetectors and so on, you can use either direct or indirect semiconductors, but for sources, you do need a direct band gap semiconductor. And the reason for this is that, as we'll see later, in a source, you have emission of light associated with the downward transition of electrons which are originally in the conduction band and make this downward transition to the valence band, and the energy difference that the electron loses is given off as a photon. So it emits light either spontaneously or in a stimulated manner, but so the electron needs to make this downward transition here. And if the border of the bands are misaligned, the electron which is up here in the conduction band, besides giving off energy in the form of a photon, needs to go through change in momentum. So in the next part of this class, we'll see that the wave vector, which typically we associate with plane waves or propagating waves, also has a relationship with momentum, linear momentum. And therefore, there's a direct relationship between wave vector K and momentum. So if the electron needs to go through a change in K, it needs to go through a change in its momentum. So somehow the momentum of the electron also needs to change, besides the energy, which would be given off as in the form of emitted electromagnetic radiation, photon. You would also need a change in momentum, and this is not very likely to happen. And therefore, it's very difficult to make light sources or lasers with indirect band gap semiconductors, because you need a change in momentum for the downward transition to take place, besides the change in energy associated with the electron. And since this is very unlikely, these materials are in general not used to make light sources. So no LEDs or no lasers, diode lasers and so on can be made with, for example, silicon and other indirect bandgap semiconductors. Okay, this is very important. So indirect bandgap semiconductors such as silicon cannot be used as light sources. Gallium arsenide, indium phosphide, and other direct bandgap semiconductors can be used in order to make lasers and LEDs. So also a few other things that it's important for us to remember is that although the lines that we've drawn in this depictions seem to be continuous, what you actually have here is discrete states which are bunched together, they're close together and distributed throughout the band structure. And these points can be farther apart or closer together depending on the position here, along the conduction band or the valence band. But these are discrete points, okay? So each point corresponds to an allowed value of energy and its corresponding allowed value of wave vector. So each point is a state here which will have associated with it a k value, okay, a wave vector, which we'll see also has a relation with momentum, and also associated with it an energy value. Okay, and these are discrete, and they are states. They are energy and k values which can be occupied, potentially be occupied, but are not necessarily occupied. As we said, at 0k, if you give no energy at all to the electrons of the valence band, no electrons will make the upward transition towards the conduction band, and you have all the states down here completely filled for a semiconductor, and all the states right here completely empty. Although the states are there, these are energies that can be acquired by the electrons. They will be empty. Once you give some energy in the form of temperature, electric field, or any other manner, some electrons can make the transition and occupy these states, leaving behind the empty states, which is what we call holes in the valence band.